Again, does it converge? That's the question. And you're given the sum from n equals 1 to infinity of 1 over 3n squared plus 2. This is much like the comparison test involving the indefinite integral, or the improper integral rather, that we talked about in 7.8. So if you were okay at that, you'll be okay at this. We need to figure out what we're going to compare. So the given guy, we need to figure out the given sequence of terms that we're summing. We need to figure out what to compare that to. So 1 over 3n squared plus 2. It would be nice if we can compare the given sequence of terms that we're adding together. It would be nice if we can compare that to a sequence where we know what the terms do when we add them, like a p-series, like a geometric series, something that we can easily see converges or diverges. So what's maybe it's not obvious now, but it will be. What will be the obvious thing to converge to compare this to once you get some practice in? Yeah.
Well, you have a reason squared, so maybe you just use the in power rule.
Well, the p-series, yeah, I think that's what you mean, right? Yeah. Yeah, and in fact, if you delete the plus 2 in the denominator, don't you make it bigger? Because you're making the denominator smaller. But I could go even further and delete the times 3, right? So couldn't I say that this 1 over 3n squared plus 2 is less than 1 over n squared? Would everybody agree with that? Now, we also need what? Yeah. And it can be or equal to, but I think in this case it's strict. I think these inequalities are strict here. Now, here's where students go wrong. And I'll break this up into 3 steps, just like with the comparison theorem. So it'll really be reminiscent of what we did right before the first test. Now, we want to say something about the sum involving 1 over n squared, the thing we're comparing the sequence 1 over 3n squared plus 2 to. But it's got to be the sum, not 1 over n squared. So here's the biggest mistake I will see on the test. I will see somebody say 1 over n squared converges because it's a p-series. But 1 over n squared is not a series, is it? It's a sequence. And even though you were probably, whoever does this is probably thinking kind of the right way, they're writing it incorrectly. And it's my job to tell them that. So no, so what do we need? We need in the second step, first step is all about the inequality, getting the inequality right, and getting the sequence we're comparing the given sequence to, getting that right. So it's all about that inequality. And the second part is making a conclusion about the sum involving the sequence you made up or you derived from the given sequence. But it's got to be the sum. So how are we going to say it? It's the sum from n equals 1 to infinity of the 1 over n squared. And if you want, you can have some kind of statement that connects everything, like now or next or whatever. So you could say now. This sum, the sum from n equals 1 to infinity of 1 over n squared does what? It better converge because you're comparing the given 1 over 3n squared plus 2 to something bigger than it, which means it better converge. I'll say more about that in a second. So converges. And what's your reasoning? Well, we didn't say it's a p-series yet. If you said it's a convergent p-series, then it would be okay just to say p equals whatever, which is greater than 1. So it's a p-series. You should make that statement somewhere. I'm going to do it within the parentheses, within the explanatory parentheses. And then p-series, I should state what p is. P equals 2, and a little more explanation, it's greater than 1. Because it's got to be greater than 1 for it to converge. All right, so then now that's statement number 2, and then what's your conclusion? Thus, you can use some snotty sounding word, thus, therefore, hence.
3 dots.
3 dots, yeah, I never liked that, but yes, you can use that. Ergo, I like that one, ergo. That's a good one. I'm not sure that's That's one of them, is it? I like it, but I'm not sure that fits. Behold what I have done. All right. All right. I'll at least know why. Thus, and I'll switch. No, then that means you're sad that it converges. So, okay, so thus, what about the original series? Converges, thus the original series converges by the comparison test, or I would accept by comparison. Well, you know, I better put in the test because there's two different comparison tests here, so I better at least put in by comparison test. Okay? Now, the inequality is very important. Let's go back up to the statement of the theorem. If the sum involving b sub n diverges, so let me write that down. The sum involving b sub n diverges. Does that tell you anything about the sum involving a sub n? It does not, because the individual b sub n are bigger than the individual a sub n. So this result tells us nothing about the sum involving the a sub n. And what's a similar statement we could say about a sub n? Yeah. So if the sum from n equals 1 to infinity of a sub n converges, great for the sum of a sub n, right? But it tells us nothing about the sum involving b sub n. So this converges tells us nothing about the sum of the bigger terms, because they're bigger. Does that make sense? So now fast forward, or rewind, depends on how you look at it, to what I was talking about over here. Once you get this inequality, you already have in mind what your conclusion is going to be. If you're comparing the given sequence of terms that you're adding to something bigger, then you have in mind that the sum involving the sequence that's bigger is going to converge. If you're comparing it to something smaller, the sum involving the sequence that you made up had better diverge, so that your given sum diverges, right?